All right, I'm going to prove the fundamental theorem of cyclic groups. So you know this is going to be a good one. Let G be a cyclic group of order. There's exactly one subgroup for every divisor of D of n, and there are no other subgroups. So you know how many subgroups there are as long as you just know the order of the group. This isn't true for most groups. So I'm going to let little g be a generator of big G. And then for every divisor D, I'm going to define H sub D to be that. So in other words, if I have G is equal to maybe Z6, which is equal to 0, 1, 5, that's barely legible. I'm sorry. I can define H1 equaling, you have 6 divided by 1 times the generator 1, which equals 6, which equals 0. More interestingly, I have H3 is equal to 6 divided by 3 times 1, which equals the subgroup generated by 2, which equals 0 to 4. And so you can do H sub 2 and also H sub 6. And so you can see that you can get these subgroups. And so I'm just going to name them H sub D, where D is the divisor. And I'm going to show that these are the only ones. Take a look. Notice that if I take the dth power of this element here, I'm going to get, then I get G to the n, and n is the order of G, so I get the identity. Take any smaller power, that's smaller. So I end up with this. But look, if I get n times m over d is going to be less than 1. So n times this is going to be less than n. So I won't get the identity back because the order of n means that n is the smallest integer that returns g back to the. All right. So the order of this is d, which means HD is also d. So that's good because I want to show to you that there is exactly one element of each divisor and there are no other subgroups. So I'm showing you that there's at least one, and we're done with that. So now I just need to show that these subgroups are the only ones that we have pretty easily. So I'm going to let H be any, and I'm going to show that H is equal to HD for some D. So by the previous theorem, we have H is equal to G to the m, where m is the smallest positive integer m such that this is true. If you want, this is essentially saying that it's a result that says that every subgroup of a cyclic group is itself cyclic. And so you can find a video on this. Just look for cyclic subgroups under my channel. So let's take a look. Then that tells us that m is the smallest positive integer, so we just need to show that m divides, that m is equal to n over d for some d. And then that's going to imply that h equals h sub d. Alright, so by the same result that I told you before, you can look it up. If g to the k is in h, then m divides us. We know that g to the n is in h because g to the n is the identity. Well, what does that mean? That means that it has to be a multiple of m. So m divides n. Because that tells me that h is equal to, this is a typo. This should actually be h is equal to h n over m. And I know that that's going to be an integer because I know that m divides n. So that's a typo. So we're good. It's just not equal to the right label. So d is equal to m. D is equal to m because I have this, and that's equal to h n over m. So d and m are the same. That's it. Thanks.